Good afternoon, students. So in the last class we discussed gated SR latch, right, using 4 NAND gates, right, and which is also called as a SR flip flop, which is set and reset flip flop, right. So in today's class we will see the modified version of SR flip flop, which is called a gated D latch or a D flip flop, right. So I can call it as either D flip flop, or I can also call it as the gated D latch. Okay, so it is very simple. It is same as SR. It is same as SR, where we used 4 NAND gates, right. It is same as SR, but in gated D flip flop I have gated D latch, I have only one input, that is D, right. So what happens here? You draw the same circuit of SR, okay, Q bar, and here see, this we have denoted as S, and this is the control input, which is called as clock, and this was R, right. So this was the circuit of SR flip flop. Now to convert this two inputs into one input, so what I'll do here, I'll put one NOT gate here, that's it. So this is the circuit of gated D latch or a D flip flop, right. So now this input will become D, right. So this D stands for either data or a delay, right. So you can either call it as delay flip flop or a data flip flop. Why it is called data flip flop? Whatever input you give here, the same output will be you will get the same output, or that flip flop will store the same input, right. So if D is equal to 0, the flip flop will store 0 after applying clock. After applying this controls input, the flip flop will store 0. If I make D is equal to 1, the flip flop will store 1. So this is the meaning of data flip flop. And why it is called delay flip flop? It will undergo a propagation delay, a little time the input will take to travel from input point to output point, hence it is called the propagation delay, right. So now we will analyze this circuit. So let us name the NAND gates, right. So now instead of SR, I have only one input, that is D, and one control input, which is clock, and outputs are Q and Q bar, right. So here there is only one input, means you have only two combinations. One is either 0 or 1, sorry, 0 and 1, right. So here will now I'll keep D is equal to 0. So when D is equal to 0, that means S is equal to 0 and R is equal to 1. That means the flip flop will reset, right. See, if D is 0, the output of first NAND gate, I'll apply the clock pulse, right. So clock pulse, clock will look like this. It's a square waveform, right. So and it has two levels, where the level is low, it is denoted as 0, and when the level is high, it is denoted as 1, right. So we are applying clock is equal to 1 to get the correct output, right. So here so we'll apply the input, which is which D is equal to 0, and we'll apply the control input, where in which control input is equal to 1, right. So now after applying this control input, what happens here? Since D is 0, this input will become 0, and clock is 1, this input will become 1, right. So 0 and 1, 0 NAND 1, output of third NAND gate will be equal to 1, because one of the input is 0, right. And since D is 0, output of this inverter is 1 and clock is 1, so 1 NAND 1 is equal to 0. So what happens here? The output of fourth NAND gate will be equal to 0, and since one of the input for second NAND gate is 2, second NAND gate is 0, the output of second NAND gate is 1, since one of the input of second NAND gate is 0, right. So Q bar is equal to 1, right, and this one is applied to one of the input of second NAND first NAND gate. So 1 NAND 1 is equal to 0. So that means when clock we apply when we apply the control input and D is equal to 0, the flip flop will store 0, right? So what value the flip flop stores, that will be highlighted by the Q output. If Q is 0, then flip flop stores 0. If Q is high, then flip flop stores 1, right? And Q bar is equal to 1, right? Now we will apply the second input where D is equal to 1. Since D is equal to 1, S is equal to 1, that means this input will become 1 and the output of inverter will become 0. Since one of the input of fourth NAND gate is 0, the output will become high, right? And 1 NAND 1, output will become 0, right? Since one of the input of first NAND gate is 0, output will become 1 without any delay, right? It will not wait for the second input, right? So this output is 1 and this 1 and this 1 NAND 1 is equal to 0, right? So when D is equal to 0 and we apply control input, what we will get? Q is equal to 1 and Q bar is equal to 0, right? So this is the gated D latch, or we can also call it as D flip flop, right? And this is the truth table. This is the truth table of D flip flop. Okay, this is truth table of D flip flop. Next, we will move to the next slide where we are going to discuss one more flip flop which we call it as a Jack and Kilby, right? So in short, we call it as JK flip flop. Next flip flop is JK flip flop, or which is also called as gated JK latch. So what is the disadvantage of SR flip flop? As we have already discussed SR flip flop, for last combination when S is equal to R is equal to 1, we will get Q is equal to Q bar is equal to either 1 or Q is equal to Q bar is equal to 0. In case of SR latch, we got, or SR flip flop, we got Q bar is equal to 1, and in case of S bar R bar flip flop or get S bar R bar latch, Q and Q bar is equal to 0. So which are not complement to each other, right? So this state is called as the forbidden state. This state is called as the forbidden state. So to overcome this forbidden state, we are going to take the help of JK flip flop, right? So SR flip flop. So in SR flip flop also we had this forbidden state as well as in SR latch, right? So to overcome that forbidden state, to avoid this forbidden state, we will go with the JK flip flop, right? So again, the for all these D flip flop, T flip flop and JK flip flop, the circuit remains same. Only little modification you have to do, right, to get the other flip flop, right? The same circuit we used for D flip flop, right? And in between S and R we connected one inverter, right? So here what modification takes place, that we will see now. Okay, so this is Q, this is Q bar, and one input is control input which we call it as clock. Second input is, instead of S and R, you denote the inputs as J and K now, right? So now this is the modification in SR flip flop. To convert SR flip flop into JK flip flop, so we are going to connect again this Q and Q bar to these two NAND gates like this. So these are, let us name the NAND gates, right? So this is the circuit for a JK flip flop, right? So here how we are going to avoid this forbidden state, we will come to know. Okay, now what I'll do, instead of SR, we need to write now J and K, right? And input, one more input is control input which is clock, and two outputs Q and Q bar. Now if I make J is equal to 0, K is equal to 0, and if I make control input is high, let us assume the previous state as 0 1, right? So we will analyze the circuit and let us check whether this state will remain as it is or no when j is equal to 0 and k is equal to 0. So when both inputs are 0 or when one of the input when one of the input is 0 for NAND gate, the output of those NAND gates will be equal to high, right? And when one of the input is high for a NAND gate, then it will wait for the second input, right? So if second input is 0, then output is high. If second input is 1, then output is 0, right? See now, for fourth gate, Q is 0, so second input will be 0, so output of fourth gate will be equal to 1, right? And since Q bar is high, which is connected to second input of third gate, so 1 and 1, Q is equal to 0. That means output will remain in its previous state. That is, there is no change in the state, right? So if previous state was 0 1, then now we will assume one more previous state, that is 1 0, right? So if Q is equal to 1, Q bar is equal to 0, we will again check, we will again analyze the circuit and let us check whether this state remains same or no, right? So let us apply the clock input as 1. Since one of the input is 0 for gates 1 and 2, output of those gates will be equal to 1. Now since Q bar is 0, I am taking this state, right? Since Q bar is 0, which is connected to one of the input of third NAND gate, so output of third NAND gate will be equal to 1, and this input is connected to fourth NAND gate, so 1 and 1 is equal to 0. That means the output remains same in its previous state, right? So there is no change when j is equal to 0, k is equal to 0, and the same state we got, that is no change state we got even for SR flip-flop, right? So we have modified, we have taken the modified version of that SR flip-flop and we converted into JK flip-flop, right? So for first state, I'll write it as no change. There is no change in the state. So whatever previous state you assume, it will remain in its previous state. Next, I'll make j is equal to 0, k is equal to 1. So here I am treating this j as yes and k as r, right? So now r is 1 means the flip-flop is going to reset, okay? So that we will verify now. So now here I'll make j is equal to 0 and k is equal to 1, right? So here I'll assume the previous state as 1 0, okay? The previous state I'm going to assume as 1 and 0, right? See, if j is 0, one of the input of first NAND gate is 0, that means the output will become high. So it will not wait for the second input to come, right? Next, when k is 1 and control input is also 1, right? So when both inputs are 1, the output of that particular NAND gate will depend on the third input, right? So what is the third input, which is connected to Q? Q is equal to 1, so all three inputs will become high and the output of second NAND gate will become 0, right? So since the one of the input of fourth NAND gate is 0, output of fourth NAND gate will become 1, correct? Now this Q bar is connected to the second input of third NAND gate, so this input will become 1, so 1 NAND 1 is equal to 0, right? So what you got, when the control signal is high and when k is equal to 1 and j is equal to 0, we got the reset state. This is called the reset state. That means the flip-flop is going to store 0, right? So now this 0 1 will act as the previous state for the next state. If I change j and k value, right? So for that state, the 0 and 1 will act as the previous state, okay? So now I'll make j is equal to 1. I'll erase these intermediate values, just wait. So we will take the third case where j is equal to 1 and k is equal to 0. J is equal to 1, k is equal to 0, and we will apply the control input, which is 1, okay? We'll make j is equal to 1, k is equal to 0, and the previous state what we are going to assume, it is 0 and 1, right? Now we will analyze the circuit. Since one of the input of second NAND gate is 0, output of second NAND gate will become 1, right? And two inputs of first NAND gates are 1. That means the output will depend on the third input. So third input of first NAND gate is connected to Q bar, and Q bar is high, right? So all three inputs of first NAND gate will become high and the output will become 0, right? Now, since one of the input of third NAND gate is 0, output of that particular NAND gate will become high, right? So what we got here, Q is equal to 1, and this Q is connected to second input of fourth NAND gate. So 1 NAND 1 is equal to 0. So what you got for J is equal to 1 and K is equal to 0, we got Q is equal to 1 and Q bar is equal to 0, right? So now we understood the first three states, and the last state in SR flip flop, if I take S is equal to R is equal to 1, what you got, both outputs were either high or low, right? So now we have to avoid this state, that is forbidden state, right? So now for next state, what will be my previous state? For next set of inputs, what will be my previous state? Q is equal to 1 and Q bar is equal to 0, right? So now we will verify how this setup or how this modification avoids the forbidden state. Okay, so now we will make J is equal to 1 and K is equal to 1, right? So if I make J is equal to 1, K is equal to 1, since J1 input is high, control input is also high, right? Now the output of first two NAND gates will depend on the third input, right? Since Q is 1, because the previous state was 1 0, since Q is 1, which is connected to third input of second NAND gate, and Q bar is 0, which is connected to the third input of first NAND gate, right? Since one of the input of first NAND gate is 0, output will become high, and all three inputs are high. For second NAND gate, the output of second NAND gate will become 0, right? Since one of the input of fourth NAND gate is 0, Q bar will become 1, right? And this one is applied to the second input of third NAND gate, so 1 NAND 1 will become 0, right? So did we avoid the forbidden state? Yes, because now Q is 0 and Q bar is 1. That means Q and Q bar both are complement to each other, right? So when I make yes, J is equal to 1 and K is equal to 1, and if I apply the control input, what will be, if my previous state is 1 0, then my next state will be equal to 0 1, right? So again I will show you what happens if my previous state is 0 1, right? I will keep J and K is equal to 1, and then I will apply the control input. What we will get here, that we will see now. Okay, so now for this set of input, this 0 and this 1 will act as the previous state, right? So I'll keep J and K is equal to 1, right? And control input is equal to 1. Now the third input Q bar is 1 here and Q is 0 here, right? So the output of second NAND gate will become 1, output of first NAND gate will become 0, and this 0 gives you the output of third NAND gate, which is equal to 1, right? And this one and this one NAND 1 will become 0. So Q will become 1 and Q bar will become 0. That means again we got the complemented state, right? So hence we avoided the forbidden state. So in these two states you can check, when both J and K are high, we got a complemented states, right? So one state is 0 1, second one is 1 0. So if I keep this J and K continuously high, and if I go on applying the control input, what happens, we are going to get these states repeatedly, right? So these states we are going to get repeatedly. So and these states we call it as toggle states. The flip flop is going to toggle, right? That is JK flip flop is going to toggle when J is equal to 1 and K is equal to 1, right? And this is also a disadvantage of JK flip flop, right? So how to overcome that? For that we are going to use what? JK master slave, right? So that we will discuss it in next class. Okay, thank you.